Well, hello, everybody. My job is to tell you about meteorites, which have already been mentioned by the previous speakers. And I'm going to try to show you what meteorites can tell us about the asteroids. So we've already heard a little bit of what meteorites actually are. They're mostly leftover pieces of the solar system, that were the early solar system that was formed about 4.5 billion years ago. And you can see here several very large and well-known asteroids, meteorites, the Hoba meteorite in Namibia, the El Chaco meteorite here. Both of these are metal, iron meteorites, and the larger ones tend to be metal. And then the smaller ones tend to be either metal and silicate, metal and olivine in this case. This beautiful yellow colored mineral here is olivine, the rest of this is metal, or completely composed of the silicate minerals, the rocky minerals. So you've already heard where meteorites come from. They come from asteroids. They come from asteroids that are in the asteroid belt. I say mostly because there are some asteroids, sorry, there are some meteorites that come from other planets like Mars and the Moon. But meteorites in the asteroid belt were ejected from the asteroid belt either by collision with other asteroids or by the gravitational effect of Jupiter. And then they are disturbed in their orbit and they move into the inner part of the solar system where they become near Earth objects. And that's really what I'm going to talk about. So just to remind you again of the nature of the inner part of the solar system, we have the sun at the center and the rocky planets, Mercury, Venus, Earth, and Mars. And then the main part of the asteroid belt is shown here in white, between Mars and Jupiter. And this is an image that we never see because we're looking down on the solar system from above the North Pole of the sun. So this is what I like to think of as an alien's eye view of the solar system. However, we don't just have the main asteroid belt. As has already been mentioned, we have near-Earth objects. And the near-Earth objects are very well known now because we are aware of the threat of impact that was talked about earlier. So this image is a close-up of the solar system, the sun in the middle, and then I have highlighted Earth in red and Mars in blue. All the red dots inside the orbits of Mars and Earth, those are the near-Earth objects. And the green dots, of which there are far more, are the asteroids in the inner part of the main asteroid belt. Now, how can we be sure that we know that meteorites come from the asteroid belt? Well, we track them. And this is a diagram showing, again, the red ellipse is the Earth's orbit, the blue ellipse is Mars's orbit. We're looking down on the sun, which isn't marked. And the black ellipses, these black ellipses like this one here with names on them, including Tagish Lake, those are the orbits of some recent meteorites. And you can see that at the point that they are furthest from the sun, they are most definitely in the asteroid belt. Now, we've already heard a little bit about this asteroid. The first Earth-colliding asteroid that was actually detected before impact was 2008 TC3. It was detected by the Catalina Sky Survey. It broke up in the atmosphere. We have pictures of its vapor trail. It landed in Sudan. Unfortunately, the resulting meteorites were collected by US and Sudanese scientists who went out into the desert and found about 600 meteorites. I'll come back to this particular asteroid later, I hope. So there's a traditional classification of meteorites, and the traditional classification is based on what they're made of. So we have the iron nickel meteorites. They have almost no silicate minerals in them. And they probably come from the core of a differentiated asteroid. So there's also a rarer group of stony iron meteorites. And these contain, as I showed at the beginning, this lovely orange crystals of olivine, and they are embedded in iron. And then we have the slightly less spectacular, but equally interesting scientifically, stony meteorites. And these are composed entirely of silicate minerals. And one of the meteorites that I find, one kind of meteorite that I find absolutely fascinating is this type of rock here, which is called a breccia. And you can see that it's made of lots of tiny pieces that have got different colors to them. And this isn't just an optical illusion, they are indeed different bits of rock. So if you like a bargain, you go for the breccias, because in one piece of rock, one meteorite, you can have hundreds of different rock types. Now, another way that we can relate asteroids to meteorites is using the spectral type. And the spectral type is, in fact, the reflectance of the asteroid at different wavelengths. And wavelength is on the horizontal axis here, and reflectance up the vertical axis. And we can see there's a set of triangles right at the top here, which are the observation of an S-type asteroid, and then offset, so that it's easier to see, we have the spectrum of an S-type meteorite. Same with the two in the bottom section of this diagram. We have a V-type asteroid in the triangles and a V-type meteorite in the circles. Now, before you start writing in and asking questions, well, why are they actually different? The reason is that we have a thing called space weathering. And space weathering affects asteroids because they are airless bodies, they have no atmosphere, they're directly open to the space environment, and we get huge amounts of solar wind and even galactic cosmic rays impacting on the surface, and that can change the actual reflectance of the asteroid. So we do have to take this space weathering into account. But when we've done that, down here in the table, there's a set of classes of asteroids, C, S, M, B, and V. And those actually are related to what we think the asteroid is made of. So S is a silicious asteroid and M is a metallic asteroid. And then there's an example in the third column of what kind of asteroid we might be looking at. And then in the fourth column, where it says probable meteorite type, this is our best guess as to which kind of meteorites come from which asteroid families. And you can see about halfway down that in the metallic asteroids, the M class, of which Psyche is a very good example, we have an equivalent of the irons and stony iron meteorites that I already introduced you to. And here they are again, the stony iron and iron meteorites, and we think that they came from the core and close to the core mantle boundary of a small differentiated asteroid, an asteroid that was warm enough, hot enough to start to melt and to become layered inside. And so just like the Earth, we think asteroid 4 Vesta has a core which is composed of metal, a mantle that is composed largely of olivine, that lovely orange mineral that you can see there on the left, the bottom left, and it has a thick crust as well. And we get a number of our meteorites come from the surface of the planet Vesta. Now, Vesta is a differentiated asteroid. In fact, it may be the only remaining differentiated asteroid, because possibly all the others have broken up in some way. And our reason for saying that is that we have hundreds of different types of iron meteorite. So although you can put some of those together chemically and they look like they've come from the same parent asteroid, there are still over 100 that are not related to any other metal meteorite. So we might have hundreds, if not thousands, of metal asteroids out there, which are the remnants of the core of previously differentiated little bodies. Now, one of the ways in which we study meteorites is to take them to our electron microscope. And this is a picture of a couple of stony meteorites, or the same stony meteorite, but shown in two different ways. Now, stony meteorites are often left over from parent asteroids that did not do this melting thing. They were not differentiated. They're left over after planet formation. They were never involved in forming any kind of planet, or they did form asteroids, but they're quite late in accreting. And one of the interesting features about these stony meteorites is that they contain these little spheres here are what we call chondrules. So the picture on the left is called a backscattered X-ray image, and it is used to for us to look at the detailed internal structure of a meteorite. On the right is what we call a false color image, where we look at the X-rays that come off this meteorite when we bombard it with electrons, and we see that the X-rays for the element magnesium we color in red, and for the element iron we color in green, and for the element sulfur, in this case, we colored in blue. And you can immediately see that there's a bit of iron here because it's bright green, and you can see these magnesium chondrules are full of they're bright red, so they're full of magnesium, and the blue is sulfide mineral. Now I'm going to try to explain how chondrules are formed, because they are one of the most abundant items that we find in meteorites. We have a class of meteorite called ordinary chondrites, and they are usually chock full of chondrules. So chondrules are tiny spheres of melted rock, and on the left-hand side we have some microscope images of them. So these are just when you cut the meteorite into a very thin slice and you shine light through it, and you can see on an ordinary microscope what they look like. And there's lots of information that a trained person can take out of these pictures. But how did they form? Well, the one thing that we do know is that they must have had a period of time when they were very hot and they melted, because they often contain glass. And glass is what happens to melted rock when it freezes again. Instead of crystallizing as crystals, it often forms glass. And there's an old traditional, if you like, way of explaining how chondrules are formed, and it involves the accretion, as is in the top diagram with all the pretty colors, accretion of metal and olivine, and this material was then heated up. And when you heat up metal and the olivine together, you can start to melt. And this is where we get the pale blue cyan kind of color, which is the melt itself. So how they were heated is still under debate, but maybe they were heated by shock waves from the sun. And slowly they become bigger and they accrete other things. They form rims, as you can see on the right-hand side. So that's the traditional method of forming chondrules, or at least the traditional hypothesis. Science works in interesting ways. People have thought ever since the first person who looked at a meteorite with chondrules in it down a microscope, which was about 150 years ago, the very first person said, "Oh, these looks like drops of fiery rain." And we still have that basic idea that these were droplets, spherical droplets in space that were formed by melting. However, more recently, we've come up with a new idea, and that is this alternative idea shown at the bottom right-hand corner, where we have impact splashes. Now, what this means is that you have two bodies, two planetesimals, two asteroids, that collide, and they are sufficiently hot, or the collision is sufficiently energetic, that lots of melt is formed. And that may be one way in which chondrules are formed, because those impact splashes will also be spherical. They may crystallize, and they may also form glass. So that's a new way to form chondrules, and at the moment it's a subject of lively debate. Going back to asteroids, if you look at the density of asteroids, and that's shown on the bottom here, the horizontal axis, where it says density in those lovely old units of grams per cubic centimeter, you can see on the right hand side I've written the word intact, and that's where the density is around 3 grams per cubic centimeter, and that's a typical density of rocks and a mixture of rock and metal. And you'll see at the top right hand corner, there we go, Vesta. And Vesta is one of the largest of the asteroids, and it's also one of the densest. So we can make a prediction there that Vesta is intact. It is not a broken up asteroid. But as we go over to the other side, where the density is very low, and we find a lot of asteroids here, like Sylvia and Psyche, yes, these have got a low density, and we think that they are basically broken up pieces that have of the same asteroid that has reaccreted into what we call a rubble pile. Before you start writing in saying Phobos and Deimos down here are not asteroids, I bet you they are. They just happen to have been captured by Mars. So those are the two moons of Mars. Okay, so one of the things that I like to do is studying these brecciated meteorites. And why do I like that? Because they tell us what's happening on the very surface of asteroids. So we've seen things that happen in the core, and now we're looking at things that happen on the very surface. And on the left-hand side, we have a rather weathered looking meteorite, and that's because it's been sitting out in the desert for a long time. But you can see it's all made of the same stuff, and in between the blocks of this orange colored rock, you can see some black lines. Now these are black veins. They go all the way through the rock. They are actually the result of melting due to impact, melting of the silicate rock due to impact, and then they freeze, and then this all happens on an asteroid. It's nothing to do with what happens when the asteroid, the meteorite arrives on Earth. So it's telling us a bit about asteroids. And now on the right-hand side, this is the only meteorite I'm going to show you that isn't from an asteroid. This one's from the moon, and it contains a lot of different types of lunar rocks. So if you can't afford a big individual meteorite from the moon, because it's so expensive to buy one from meteorite collectors, you might look at a brecciated meteorite, because it's got all the bits of the surface of the moon in it. And it doesn't take you to be much of a geologist to say, well, that dark colored grey, dark grey, and that light grey might be different, that lump, and that's different from this lump that seems to be made of very brown and white material, and then there's another brown and white material lump here, and therefore you can get a lot of useful information out of a single piece of a brecciated meteorite. Now let's have a look at the surface of a real asteroid. This is Bennu. You've heard about Bennu, and these are images from NASA's OSIRIS-Rex mission. They only came back a few days ago, so they're quite up to date. Look at the scale. In some places, we're looking at things that are less than half a meter across. A little white box is less than half a meter across. And the NASA scientists have actually put on some little yellow lines here, little arrows that are pointing to where the surface rocks have been fractured. So I think it comes as no surprise, although I couldn't show it on the previous couple of diagrams, that Bennu looks like a very fractured asteroid. It's a rubble pile. So far, we've only managed to visit one asteroid and bring a bit of rock back to Earth. This was done by the Japanese. They visited the asteroid Itokawa, and their Hayabusa mission touched down on the surface of this S-type asteroid, as you can see in the top left-hand corner where we have an artist's impression. And Hayabusa means falcon. And it basically was swooping down over the surface of the asteroid and grabbed a sample. Unfortunately, it didn't grab a very big sample, but Japanese scientists didn't worry too much about that because they got enough for them to do a lot of science. So up in the middle, this grey image in the middle is a particle from Itokawa. This is an electron microscope image again. And once again, we can see the mineral olivine. So we know that there's lots of olivine on asteroid Itokawa. And in fact, they were able to do this other thing with an electron microprobe, in which in the bottom right-hand corner, they've shown us the olivine composition, and it's just described as the amount of Fa in the olivine, so we don't need to worry about what that means. And you can see from the histogram that almost all of the particles that they've analysed fall in a field called LL. There's also a field called L and a field called H, and these are the ordinary chondrite fields. So now we know that Itokawa asteroid is the same as LL, ordinary chondrite meteorites. So where next with asteroids and meteorites? Well, as has already been mentioned, Japanese probe Hayabusa 2 is already on its way, bringing pieces of the very dark asteroid Ryugu back to Earth. And we're wondering whether it will look like the carbon-rich meteorites which we have in our collections. NASA's OSIRIS-Rex mission is bringing back pieces of a B-type asteroid, asteroid Bennu. This is another carbon-rich asteroid, and we don't know whether it will be the same as Ryugu or different. We'll have to wait and see. We know, however, that there are several kinds of carbon-rich meteorites, and so bets are on for what kinds we will find on Ryugu and Bennu. And of course, we might actually find something that is not in our meteorite collection. I think that's very, very exciting. And in fact, going back to the asteroid 2008 TC3, in that material that fell to Earth as meteorites, we have already found several kinds of meteorites that were not in our terrestrial meteorite collection. So we already have found some new meteorites from an asteroid impacting the Earth. So the last thing I want to mention is the mission to asteroid 16 Psyche. Now, this will be the first to visit a metal asteroid. Psyche is an M-type asteroid, but this is unfortunately not a sample return mission. But it will investigate Psyche very closely. It will try to make analyses of the surface, and we're hoping that we will find that Psyche looks like some of our iron meteorites. I've shown one here on the bottom, which has been cut and etched. You can see inside it's much more complicated than it looks on the outside, with several different kinds of crystals in there. Now, for those of you who are interested in the possibility of asteroid mining, it has been estimated, not by me, but by economists, that Psyche might contain $700 billion worth of gold and precious metals. And on that, I think I'll hand over to the next speaker, who's going to tell us about what precious materials we can bring, or we can mine on asteroids and the moon. Thank you.